So we looked a little bit at the coding theorem for classical channels and talked about the definitions of various capacities of quantum channels, just in an abstract way. Yesterday, this was day 1, day 2. Yesterday we talked about what methods should you use to describe infinite dimensional systems, bosonic systems. So let's say quantum mechanics of bosonic systems. And specifically, we looked at 4 different examples of Gaussian channels on bosonic systems that I'll just write down here to remind you of. Okay? So we had an attenuation channel. I'll just describe how they behave on Gaussian states. But based on that, you can figure out what the Krauss operators and stuff are and explicitly find out how they act on general states. So this is an attenuation channel. It absorbs some of the light you put in and adds some. Let me try to do it like this. And just adds some vacuum. Is this big enough? Is it okay? We looked at also an amplification channel that takes gamma and maps it to some multiple of gamma, but it has to add some noise in order to make the thing physical. We also looked at a thermal noise channel, which this is a vacuum down here. But a thermal noise channel just has some thermal state down here instead. And the classical noise channel was the final thing that we looked at, and it just maps gamma to gamma plus some identity. Okay, so this is just here? No, this needs to be G minus 1, because G is going to be positive, bigger than 1 rather. Yeah. And just as a reminder how this one of these channels is going to act, on the characteristic function of the input state, it's going to map some psi to some rescaled version of the channel with some Gaussian multiplier. So now what I want to do today is sort of put the first two days together, and specifically I'd like to look at classical capacity of these channels here. And for the most part, I'm going to be telling you about a nice paper that came out a month or two ago. Is it? Maybe a month or two. There are 2 papers actually by Giovannetti, Holivo, and Garcia-Patron. And there's another paper with some permutation and an additional Nicholas Cerf. So I'll tell you some background about these questions and then describe how you can actually compute the classical capacities of these channels using techniques from this paper. So first, I guess, what I'll do is remind you what I mean by the classical capacity of a channel. So what we're looking at is we have some some integer from 1 to capital M. And this is log m bits. And we want to do some encoding of that information into many copies of the inputs of our noisy channel. So it's going to be one of these in general. It's going to be one of these today. So you take some classical variable m, you map it into some quantum state that depends on m. You feed those through the noisy channel. And at the output of the channel, your receiver is going to do some decoding operation that they use to guess some message, or guess your intended message. And it's a good code if their guess is equal to the intended message with high probability. The rate of the code is just log m, the number of bits that you're trying to transmit, divided by the number of channel uses. We say a rate is achievable if there is some code like this that allows you to decode with high probability. And we just call the capacity of the channel. It's the maximum achievable rate for the channel. And you remember, for a classical channel, we had this nice formula for the capacity. It was just the maximum over distributions on an input x of the mutual information between x and the output y. Yes?
Rate is log m
By n. Oh yeah, so there are n channel uses here. Okay, so before we go on and try to figure out what the classical capacities of these channels are, I want to tell you about one more classical channel that's sort of the classical analog, or these guys are sort of the quantum analog of this classical channel. It's called the additive Gaussian noise channel. And what does it do? Well, it has some input random variable. It's a real variable. And it gets mapped by this channel to the original variable plus some z, where z is Gaussian distributed. So mean 0, variance, let's call it n. Now, can anyone off the top of their head see what the capacity of this channel is? Okay, so actually it's infinite at the moment, because if I know what the variance of this random variable z is, I'm going to choose a bunch of different signals that are very widely distributed, very far apart, so that it's extremely unlikely that when z gets added to x, that I would ever see an overlap with the sort of region where the different code words are non-trivial. So, if I spread out along the real line like this, and the variance of my z is like that, then these guys are just not gonna matter. These guys are just not going to overlap. I can always decode by saying, well, if my number's between here, it's this. If my number's between here, it's that, etc. So in some sense, this channel isn't well. Yeah, if. Yeah, that's right. And but if it's really wide, I would just put them even further apart. Okay, right? However, that's not fair, right? And it's not fair in the sense that if you're thinking what I'm trying to do here is, if you're thinking of this as a crude model of an electromagnetic field, and this is like the electric field, then this coding scheme I just described means I'm using enormous amounts of power to keep my signals really far apart. Okay, so what we need to do is add an additional constraint to make this more meaningful. So in this case, we're going to have many channel uses. So each code word, M, is going to get mapped to some string of x's, x1 up to xn. And again, if you think of this as electric field, the power or the energy in it is going to be something like x squared. So a natural constraint to consider is insisting that the average energy of your code word should be bounded by some p. And now what you said earlier is exactly what we have to worry about. We're forced to stay in some sphere, but what we'd like to do is make sure, the bigger the noise, the more likely the two things of a fixed distance apart are going to be caused to overlap. So now we're going to get some trade-off between the size of the noise and the power constraint that we've got.
Is this what is called wideband?
No, this is like narrowband, yeah. Right, we have like some fixed frequency basically, and this is the electric field at that frequency, say, or the power at that frequency. You can use this formula eventually to calculate wideband capacities too, if you want. Okay, and in this case, now the capacity of the channel is just given by the maximum mutual information between, we'll call this y, x and y. But now we have to optimize over x that satisfy this constraint. It has to have energy less than p. So now this is the capacity of the channel and also the amount of power I'm allowing. And actually, let me just write out explicitly what the answer is here. You can figure out what it is. The optimal variable is just some Gaussian also. Some Gaussian, the optimal x is some Gaussian. Its variance is determined by this p. And if I have a Gaussian random variable, call it x, well, let's call it x. If it has variance sigma squared, then the entropy of such a variable is just going to be log 2 pi e times sigma squared. Okay, so let's just compute what's going to happen here. So this mutual information, if you remember, is just going to be equal to the max over e x squared less than or equal to p of entropy of y minus entropy of y given x, where this thing, remember, was entropy of xy minus entropy of x. And then for this particular channel, we can compute these two things. We know if we're going to take x to be a Gaussian, that the sum of the two Gaussians is going to be a Gaussian with variance equal to the sum of the two variances. Okay? So we know that this y, the variance of x is going to be p, the variance of y is going to be n. So the variance of this whole thing is n plus p. And then we can use this formula, which tells us that this entropy h of y is going to be log n plus p times 2 pi e. Now, conditioned on x, when I know x, the conditional distribution on y is just going to be z. Right? So it's going to have a variance of n. So for this term, I'm always going to get just log of 2 pi. Oh, I forgot a half here. Log of 2 pi e times n. And that gives us the capacity here now of log 1 plus p over n. Half. Okay, so this you can see, depending on how much power I'm allowed, I get more capacity. And what matters is the power that's in the signal compared to the power that's in the noise. Right, and if I have like much more power in my signal than in my noise, you see that I can get sort of multiple. Well, you can see if I have comparable signal to noise around 1, I'm not going to get much capacity. But if I let this grow, the capacity also grows. So our goal really is to figure out how to find an expression like this, but for these channels now instead of this additive Gaussian noise channel. So before we go on, are there any questions? Oh, yeah. Pardon?
If you consider Gaussian channel H with a spread sigma,
Mm-hmm.
the entropy is something like that, half log by sigma squared.
Half.
Say what is the entropy?
How the expression of the x, how it comes?
Oh, okay. Well, we have the probability distribution. This is actually called differential entropy. It's roughly the same as the regular entropy, but it's for continuous variable, and you just integrate this. And for a Gaussian, you can just figure that out, right? This is e to the minus x squared over 2 sigma squared, and this is an x squared. So that integral you can do, you just do the thing where you integrate that and you take a derivative and it comes out.
Perhaps the variance of the noise dictates the size of
The variance of the noise, right? Because you can imagine what you kind of need to do is make sure that each of the code words you choose, when they get corrupted by some typical set of noise, they don't leak over into the decoding sphere of some other code word.
But you need n. You cannot do it less than n.
That's right. Well, I mean,
The size of the code word.
oh, the size of the code word needs to be, it's going to need to grow. You can't just do it with a single channel and hope to do some useful coding there. Okay. Okay, so now let me just, pardon? Oh, okay. What should I do? Oh, I see. Can I maybe attach it to my shirt? Oh, I see. I should take it. Oh, okay. Yeah. Sorry. Is that okay? Okay. Okay. So now I want to say just a few words about this Holovo information. I think maybe I didn't even use the phrase on the first day because we were at the very end discussing classical capacity of quantum channels. But the point is, there's some quantity kind of like this mutual information that tells you what is an achievable rate for classical communication over classical or quantum channel. I think you'll see a proof of the achievability of this quantity later. I think Pranav is going to talk about that. But for now, let me just remind or tell you what it is. Okay. So for a quantum channel, chi of n is just defined as the maximum over some probability distribution on x, some classical variable x, and some input ensemble, some collection of quantum states that are like inputs to the channel, and it's the mutual information, this xb, evaluated on this state rho xb, where rho xb is just this state. It's the thing that happens when you choose a random x. According to x, you prepare some phi sub x, and then you apply the channel to that phi sub x. And this mutual information, I guess I should just explicitly write again. It's the same formula for mutual information in terms of entropies, but now these are these von Neumann entropies. H of x plus h of b minus h of xb. So fact one that we know that I mentioned about this Holovo information, it's an achievable rate. So that means if you can find some ensemble that gives you a particular value of Holovo information, you can use that in the limit of many copies to find classical coding strategies that achieve low probability of error and that rate. It's basically by the same kind of random coding that we discussed for the classical coding case. So you can actually do a little better than that. You can find an expression for this classical capacity, and it's given by a limit of many copies of the channel. You evaluate this Holovo information on many copies of the channel and normalize by the number of channel uses. And then you can get the classical capacity itself. Now, this is called a regularization. Oh. And the trouble is, while it wasn't so difficult to compute this Holovo information on a single use of the channel if the channel is small, even if you're dealing with a small channel and you want to compute the classical capacity using this formula, you have this limit that you have to evaluate.
The inequality in the second equation, is it in the correct form?
This?
This Holovo quantity is the lower bound?
Yes, this is a lower bound for capacity because this is an achievable rate. We know how to code for it, but we don't know if that's the optimal rate. Right? And there could be something better which would make the capacity go up. And indeed, in some...
Also one knows that for single shot one cannot do better than pi.
That's right. If you restrict your attention to coding strategies that don't have any entanglement between the different channel uses, then this is exactly equal to the optimal communication strategy. Okay, and the fact that you write it like this actually is related to that, what you just mentioned, which is there exist channels that for which this is strictly smaller than the capacity. And what that means is when you're trying to figure out a coding strategy for your channel n, you have to use entangled code words in order to achieve the capacity. That also makes it very complicated to compute the capacity of a quantum channel because you need to be able to do this regularization, and we really don't know how to do it. So actually, the goal by the end of today is to show that for the particular channels I mentioned over here on the left earlier, these Gaussian channels, that this regularization is not necessary, and actually the single-shot Holovo information is exactly equal to the capacity of those channels. And furthermore, we can evaluate that Holovo information explicitly.
So suppose you want to write down the corresponding phi of n tensor n. So the only thing which will change in rho xb would be phi of x, which will now be states on the larger number space, n tensor n active. The rest of the expression, x will still...
Yeah, x can be anything.
Yeah. That is just to take care of number of terms in the decomposition.
That's right.
So that will remain same. Only the second term would...
The second term would change, and it would sort of, when you write it down, it looks almost the same, right? You would just say a1, a2, sub n, and...
n tensor n or whatever.
Yeah, and then n tensor n. That would be like the two-letter thing, sub x, I guess. and then you have to evaluate this. But then you have to keep going and going and going, and you don't know when you don't know when you're allowed to stop. Okay, so now this is for channels without any constraint. But we're going to, for these Gaussian channels, also have to have a power constraint. So you can get a similar pair of expressions. The classical capacity of one of the channels we're interested in with a limit of energy E, or I guess let's do it in terms of mean photon number. Is going to be lower bounded. Maybe that doesn't, that's, okay, we'll do that. It's going to be lower bounded by the maximum overall ensembles that you can potentially have, but they have to satisfy the property that the expectation of the average value of the ensemble, so the average state of the ensemble, can't exceed E, and then you evaluate this mutual information on the state that, on exactly the same state for that ensemble, and we call that chi of n, comma n. And then you can regularize this to find the capacity of your channel. Actually, and then it's just equal to, again, this limit as n goes to infinity of this chi 1 over n times this chi of n tensor n. And I'm going to go back to make it a little easier to discuss. Oh.
These ends represents a Gaussian noise.
Yeah. So I'm going to change the notation because this is absurd. Okay? We're going to have a limit on the energy, E. And that's chi of NE. This is actually true for any channel. But we're going to be interested in this quantity for specifically this Gaussian, where this is a Gaussian channel. But you can imagine doing exactly the same calculation for some non-Gaussian channel, and you would get this regularized expression. What's going to be nice is that we can sort of really compute this quantity for those Gaussian channels we discussed.
So the constraint is on the inputs phi x, so that the photon number has to be lower than the proportional quantity of T.
Yes. So you want to know, basically, given a budget of your mean photon number, how much information can you transmit? And you kind of expect that, that you're going to get some functional dependence that looks like this.
Phi bar is the input also.
Oh, yeah, sorry. This phi bar is just the average state at the input. Yes?
Could you please explain why is it that you need a constraint on energy or photon?
Well, I guess there are two reasons. One is mathematical, right? If you don't have such a constraint, the capacities are just infinite. And then the second is you're trying to describe what the kind of channels people actually use in practice, and you do usually, if you have a lab, have some constraint on what's the biggest power you want to put into your channel. Or it costs something more to have more power in your channel. And eventually, you start getting problems like you melt it or something, right? So it really is a sort of a relevant cost of trying to communicate how much power you're using. Looking at these quantities for the channels that we're interested in, I want to just say a couple of words about additivity. So if we have some function on channels, I'll call it f of a channel, we say that it's additive if when I evaluate that function on two separate channels, the tensor product of the channels, then it's just equal to the sum of the function on the two factors. We say it's additive. Now let's suppose that chi is additive. So what implications does that have for over here? Yeah, it all factors out. So if we have this chi of n tensor n, that chi of n tensor n, that'll just be equal to n times chi of n. The n factors out, the limit's not needed, so that means that the capacity would be equal to just this chi. And again, that's something we can kind of go off and compute, and that would allow us to figure out exactly what the capacity of the channel we cared about was. So this is a very useful property. It's also a property that's not always true. So sometimes you can find channels where chi of n tensor n is more than twice as big as chi of n.
If the n channels are correlated, necessarily a lack of correlation,
Mm-hmm.
then this will break.
This certainly breaks down if they're correlated. However, even if they're not correlated, even if they're independent, there are channels where this breaks down. Where?
When it's not a digit.
Yeah.
And you are considering only, you are not considering the correlated channels.
No correlated, all just independent channels for now. And similarly, you can put sort of a power constraint into the function and have an analogous notion of additivity. And what we want to show today is the additivity of this quantity for the particular channels that we're caring about. So first, let me show you a simple channel for which we can show this additivity relatively easily. Okay, so we're going to look at the attenuation channel. So it's the one that does this. You've got a vacuum state, and you basically take a vacuum state and your input state and ring them off a beam splitter, and the output, if your input was a Gaussian, is 1 minus lambda gamma plus lambda times identity. Okay, and even better, let's say lambda is equal to, or lambda is the transmissivity here. Okay, so now let's say lambda is equal to 0. That means that the way the channel works is it just maps gamma to gamma, or it just maps your input state to itself at the output. So let's look at what the mutual information between input and output is going to look like. So now we pick some p of x, phi of x on n copies of the channel. And this mutual information is going to be equal to entropy of the b to the n minus entropy of b to the n given x. But I can always choose these guys to be pure states. So the conditional entropy given x of b to the n is actually, in this case, going to be 0, since we have a pure state ensemble. It's just the average entropy of all the input states. They're all pure at 0. So in this case, we're just going to get that mutual information is equal to the entropy of v to the n. But now there's this constraint that we had to include. Oh, sorry. There's this constraint that we had to include, which is maximum. We have to do maximum over ensembles of phi n sub x that satisfy this constraint is less than n times e. And now, instead of the mutual information, we computed it for this pure state ensemble. Mutual information is just going to be the entropy of v to the n. And this is, under an energy constraint, if you want to maximize the entropy, this is something Fernando mentioned in his talk. I think he called it Jane's principle. Jane's principle. And basically, the fact is that thermal states maximize entropy for a fixed input power constraint. And actually, because it's a thermal state, this is actually the sum of all the individual Hamiltonians of the individual modes. The thermal state, because these Hamiltonians don't interact with each other, is just a product of a bunch of thermal states on the individual modes. So the maximum, the average state that maximizes this entropy is actually just a Gaussian state. It's thermal, and it has covariance matrix 2e plus 1 times the direct sum of all of these identities. Okay, so what's the entropy of this thing? We learned how to calculate that yesterday. The entropy of a single thermal state is just this g function of the average photon number, but there are n copies of it, so we get this extra n. And now there's a bit of fussing around that I think for now I'm not going to worry about, but it has to do with the extra factor of a half. So maybe this shouldn't be e, maybe it should be like e minus a half. So we can make sure to get all the little all the details right about that. Maybe we can discuss it in a tutorial session just to make sure we get it all exactly right. Okay, so this maximum entropy is going to be n times this g of e, where you remember g of e was equal to e plus 1 log e plus 1 minus e log e. So this is the n-shot Holovo information. We have to normalize it by the number of channel uses. So that tells us that the classical capacity of this this perfect attenuation channel, this perfect channel, is just going to be this g of e. Okay, so now we're going to use this to figure out the answer for lambda not equal to a half, or not equal to 0, for these attenuation channels.
But this is purely attenuation, quantum limited.
Pardon?
This is purely attenuation, quantum limited.
Yes. I mean, this specific one, there's not even attenuation, right? It's just identity channel, no attenuation. But now we'll do the attenuation. So now what I want to do is look at this attenuation channel with lambda not equal to 0. And I want to do two things. First, I want to get an upper bound for the capacity of that channel, and then show we can saturate it using a simple coding strategy. So specifically, we have to remember that a thermal state is going to look like I take just a vacuum, I displace it, with Gaussian distributed kicks. I guess there's a 2 pi. I can't remember. I think it's squared. Okay? So this is going to be the average state of an ensemble where I have some Gaussian distributed probability distribution. Now x is going to be labeled by these x's. And the pure state associated with a given xi is just going to be the coherent state with that displacement xi. And we want to look at what this Holovo information is going to add up to for this ensemble. So it's going to be entropy of B to the n minus entropy of B to the n given this xi. Now the nice thing about coherent states is that when you attenuate them, they're still coherent states, right? They stay pure. Okay? So again, if I tell you which state you've got, the entropy of the output of the channel is still going to be 0. So this term is going to be equal to 0. So now our problem becomes we want to maximize, well, if we're going to stick to coherent states, we want to maximize just the entropy at the output. So if I have a mean photon number constraint of E, again, the entropy at the output is going to be, well, the mean photon number at the output is going to be this 1 minus lambda times the original mean photon number. And by maximizing this entropy, I'm going to get an achievable rate, at least, of 1 minus lambda times E, of G of 1 minus lambda times E. Now we know no matter what coding strategy we use, the output power is going to be or the output photon number is going to be 1 minus lambda. It's going to get attenuated times E. And this is actually the classical capacity of a perfect channel with exactly this mean photon number. So there's no way by using some clever coding strategy for this attenuation channel that we're going to be able to exceed that. We're already achieving the perfect capacity for this mean output photon number, even though we have this channel in between. So there's no way we're going to be able to go beyond it, and we can get the classical capacity of this attenuation channel with attenuation 1 minus lambda, again, to be 1 minus lambda, and energy constraint E, it's going to be just this G of 1 minus lambda times E. And I just want to remark on something that we're going to move towards now, which is, in general, there's a close connection between this term, the minimum output entropy, or the output entropy of the channel, given the input state, and its additivity, and the additivity of this Holovo information that we saw earlier. Okay, so what I want to tell you now is about the following quantity. The minimum output entropy of a channel is just the minimum over all pure states that you put in, you could put into it, of the entropy of the state that comes out of the channel when you put that pure state in. And for channels like the ones we showed, which are phase covariant, meaning that if I apply a rotation at the input, I can undo it by applying a counter rotation at the output. This thing, the minimum output entropy, is going to be the quantity that you need to understand in order to understand the additivity of this Holovo information. So the claim that I want to show, and for the channels that we discussed, so for attenuation, we're done. For attenuation, we're done. Remember, the minimum output entropy of an attenuation channel is 0. The optimal input state is any coherent state. For thermal and quantum limited amplifiers and classical noise channels, we're going to have to do a little more work, but the answer is going to be also the optimal state to put into these guys in order to minimize the output entropy is going to be a vacuum state. So the result is going to be that if I minimize over all states, we have to insist that the states have finite energy. The entropy of the output of n copies of the state, it's going to be equal to the entropy of n acting on n copies of a vacuum state. And that's just equal to n times the entropy of the channel, rather, acting on a vacuum state. Okay, and before we get started on this, I'll make two observations about this quantity. The first is that the entropy of the output, the output entropy, is minimized on pure states. That's because of the concavity of entropy. And the second observation is that let's say I have a noisy channel, n. I can always think of it as I put some input state in, psi. I append some fixed pure state. I do some unitary, and then I do a partial trace. Call this E, call this B. So the nice thing about this is if I'm interested in the minimum output entropy, if I call the channel, the primary channel I'm interested in, N, then there's a secondary channel I can call N hat, the complementary channel, where I do the same unitary here, but I just trace out B and look at the mapping from the input to the environment. And the nice thing is, since I know that the entropy is minimized on a pure state, when I put a pure state in here, this is a pure state on BE. When I have a bipartite pure state, the entropy of one party is going to be equal to the entropy of the other. It's just going to be the entropy of the Schmidt, what's the word? Schmidt coefficients. Thank you. The entropy of the Schmidt coefficients, so that these two states are going to have the same output entropy. So for example, if I have some channel N that I can understand, I cannot understand, but I can figure out what the minimum output entropy of the complementary channel is, then I can figure out the minimum output entropy of the channel itself too. So the trick for understanding these guys is actually going to be sort of, well, there are going to be several steps, but the idea is going to be to take an arbitrary thermal channel, say, break it down into the concatenation of some channels that, that are simpler, specifically an attenuation channel and a quantum limited amplifier. Then I can look at the quantum limited amplifier. I don't quite know how to understand that. But the complementary channel to a quantum limited amplifier is sort of an approximation to phase conjugation, which happens to be entanglement breaking, which is a good thing. It lets me understand the minimum output entropy. So now I'm going to talk about entanglement breaking channels and their minimum output entropy. And it's going to turn out that the complementary channel to a quantum limited amplifier has this nice property of being entanglement breaking. Additive minimum output entropy is implied by entanglement breaking of the channel. So what should I do first?
I have a question regarding this
Oh.
complementary channel.
Yeah.
So you have some input
Yeah.
system on some input space HS,
Yep.
and your channel action goes from HS to HS.
Okay.
Okay, that's your first channel.
Yep.
The complementary channel goes from HS to HE.
Yep.
It doesn't go from HE to HE.
That's right. Right. So you should, right? Because there's only a single output. The input rather. The input is the same. I take some state, I do some unitary evolution to it, and some of it gets traced out. Right. In the case of the original channel, if it goes from HS to HS, this HE gets traced out. In the other case, it's all the sort of leftovers. HS gets traced out, so now it becomes a channel from S to E. I mean, sometimes the channel from here to there also changes the dimension of the system, right?
No, I mean, I was wondering whether your mapping is defined from HE to HE.
Oh, no, it's not, because we always, this unitary acts on A and E, but you always just put a 0 in here. You always put a fixed state in there, and the channel takes as an input the state up here, no matter what. Okay, so what's our first step if we want to prove this claim?
If it is additive, if it is entanglement breaking, then if you have entanglement in the input, that will be broken and.
Okay, this is correct. Okay, the first step is I should define entanglement breaking. Okay, so unless I mean. N is entanglement breaking if, for any state rho A prime, let's say N takes A prime to B. And then it's entanglement breaking if for any state, when I take the channel N and act on part of that state, then the resulting output state is going to be separable, meaning it's not entangled. It's just a sum over some piece of I of product states. So the point here is that these channels are very noisy. And actually, you can think of these channels always as acting in the following way. The input state gets measured, and conditional on the measurement outcome, the channel prepares some output state. Okay, so what we want to show is that if I minimize, if I take, then what we need to show is that the minimum over all input states, rho AB, to the two channels, the entropy of that, let me make sure I get it right, M tensor N acting on rho AB, this minimum entropy is equal to the minimum over rho A of the entropy of M acting on rho A plus the minimum of over rho B of the entropy of N acting on rho B. Okay, that's what we mean by additivity of the minimum output entropy. And there's an easy direction and a hard direction. Okay, so we know that this is actually always true. It's easy because one of the states that I could use here to try to minimize the output entropy of this thing is the best state for this channel tensor product with the best state for that channel. Okay, so this part is easy. The other direction is not always true, but for entanglement breaking channels, it will be true. So this is the hard part. So what we're going to have to do now is show that for any input state rho AB on these two channels, that I can find a state here and a state here that gives me some of the minimum output entropies that's at least as small as this one. Okay, so now consider any input state. Consider any rho AB. You should basically be thinking of this as the optimal state here, but we'll just show it for any. Then N is entanglement breaking, right? That means that identity tensor N on rho AB is separable. And actually, it looks like this. And I'm sorry to switch notation mid-argument, but I noticed that what I'm doing here means I'm thinking of channels M that map A to A and channels N that map B to B. So I should rewrite this, and I should rewrite this. You can prove all of these things if you have more general channels. But the point is, then I would have to write indices on everything, and it just makes it more complicated for everybody. OK, so this N is entanglement breaking. M is anything. We want to show for any state rho AB with a fixed input-output entropy here, we can do just as well by taking a state on just M and a state on just N, and still the sum of the individual entropies will be less than or equal to the entropy of the tensor product. And the point is, this is a separable state. And based on that, I'm going to introduce a third state. I'll call it sigma ABC. I'm just going to model it on this state. It's sum over I of Qi, AI, tensor B. Sorry, that should say I, BI. And this is on A, this is on B. And on C, I'm just going to put a copy of I.
So just clarification, so this AI need not be orthonormal?
No, they need not. They need not be orthonormal. And actually, the sigma I'm going to model on this channel. So I need to erase something. I'm going to define the sigma as M also is acting on this A here. Okay? So that means that sigma AB is just going to be equal to M tensor N acting on rho AB. The role of C, well, you see that it just keeps track of which term in this mixture we have. It doesn't have any real meaning other than I'm about to use the state together with the strong subadditivity property that we discussed to show that we can get a lower bound on this entropy of sigma AB. But you see, oh, sorry?
I's are orthogonal.
These I's are orthogonal, yeah. These BI's and AI's, they're not orthogonal. Does, pardon?
Is it something like an ancilla that you...
Yes, this is some ancilla that keeps track. You know, we start with some separable state, and then we don't change the reduced state by adding in an ancilla that keeps track of which term we've got. Right? We're going to trace it out sometimes and not other times, and it's going to be useful to us. Okay, so now what we want to do is apply strong subadditivity to this sigma ABC. Okay, so let's just write out strong subadditivity. You remember, it's that thing that we had with, it looks like subadditivity. Let me just remind you what that is. But it had this funny extra system running around, right? There was, let me do it in the right way. Let me do it with x's and y's. Right? It just had this extra z that was in along with everybody else. Okay, so we're going to apply this rule to this state sigma ABC. And specifically, we're going to write it in this form. Entropy of sigma AB plus entropy of sigma BC is bigger than or equal to entropy of sigma ABC plus entropy of sigma B. Let me make sure. No, it's B. I guarantee it's B. Right? Because there's always one guy that hangs around in every term, right? So if you just make B trivial, then this will be 0, then this will be AC, this will be C, and this will be A. So this is what we need, and actually we just need to rewrite it in this way. We need to take entropy of sigma AB. Remember, that's the thing we're interested in. Sigma AB was just equal to the output of this tensor product channel. And now we got a lower bound for it. It's entropy of sigma A BC minus entropy of sigma BC plus entropy of B. So now we want to figure out what this term is, because this one already looks good, right? This is already just the entropy of sigma B, so it's just the output entropy of channel N. We need to make this term look like it's the output entropy of channel M. Okay, now let's look at this state. This state, because these C's are orthogonal, this state is unitarily equivalent to a state on just the same state, but just on AC, right? because I could just condition on I, rotate this B sub I to some fixed state. Right? So, and then if I trace it out, it doesn't change the entropy because that fixed state is in a pure state. So the entropy actually of this state is the same as the entropy on just AC. So this is equal to the entropy of sigma AC. And it's the same story here. Since C has all the information about what B is and can rotate B back to some fixed pure state, the entropy of BC is just equal to the entropy of C. Now this is actually, let's see, let's make sure I get it right. Sorry, it's a little, okay. Let's see. This entropy of AC minus C is actually just going to be a sum over I, Qi, of the entropy of state A with M acting on it. Why is this? Because this, well, you can always write out a state that looks like this. You can always figure out, this is just a flagged mixture, right? These are orthogonal flags, and they tell you which state you've got here. You can always write the entropy of that as the average of the entropies plus the entropy of this system here. That's only true when the state is of this form, but it is of this form, and then we get to subtract away the entropy, so we end up with just this quantity, plus, again, entropy of N on rho B. That's what sigma B was. But now you can see that this is just the average of a bunch of entropy of output states of M. This is also just an output state of N. So both of these are bigger than or equal to the minimum output entropy of M plus the minimum output entropy of N.
Okay, we repeat once more why the entropy of ABC is same as entropy of sigma AC and
Yes, yeah. Let's see. So the state that we have is something like this.
Again, this is a very small.
Oh. Okay, and let's see how to explain this, right? So let's choose U sub I such that U sub I acting on this B sub I, which is a pure state, is just equal to 0. Okay? Then I can define a unitary on BC which just conditionally applies this U sub I to B conditioned on C being in state I. You can check that this is a unitary. Okay? So then if I take sigma ABC here and apply this unitary to it, then the state that I get is just going to be this. Right? And now, observation 1 is these two states have the same entropy. And observation 2 is if I take a pure state and append it to a state, that doesn't change the entropy either. So they have to have the same entropy. So now I can sketch the proof of this additivity of the minimum output entropy. I'll do it for a thermal noise channel. All three of these channels behave in the same way. Okay, so we'll call the thermal noise channel with mean photon number in the environment NE and transmissivity lambda, just N sub lambda NE. Okay, the first step is to notice that N sub lambda NE is equal to the concatenation of N sub lambda tilde 0 and A sub G. Okay? So what that means is any thermal noise channel I can always think of as attenuation followed by quantum limited amplification. And maybe a good tutorial thing to do is figure out relationship between lambda and NE and the G and lambda tilde. The second observation is that if I look at AG, a quantum limited amplifier, and then look at the complementary, so that's the channel where I trace out the output of the amplifier, and instead the output of my new channel is the environment of the amplifier, that's entanglement breaking. And that means that the minimum output entropy of many copies of the quantum limited amplifier is going to be, which we know is going to be equal to the minimum output entropy of many copies of the complementary channel, will be equal to n times the minimum output entropy of one use of the channel. And that's going to mean, well, so once we know that, we're sort of most of the way there. Then you have to compute what the minimum output entropy of just one use of this channel is. In that case, it's actually simpler to compute the minimum output entropy of the amplification channel rather than its complement. And it turns out that you can show that is going to be achieved on the vacuum state input. Now, that still doesn't prove everything we need to know, but it's nice because we know that the minimum output entropy of this AG is achieved on the vacuum state. Now we want to know the minimum output entropy of that. Well, the minimum output entropy of...
How do we know the minimum output entropy AG is achieved on the vacuum?
Oh, that's going to be step 4. I mean, each of these steps I'll say more about.
Okay. So that's not yet proved.
That's no, this is just a sketch of how the proof's going to work. And I think it turns out I'll tell you some more about it next time because I was hoping to do it all today, but I have a couple more boards worth. Oh yeah, so once we do know this, then, well, we want the minimum output entropy of the thermal noise channel, right? However, since it's a concatenation of some channel and the quantum limited amplifier, and we know that the quantum limited amplifier has minimum output entropy achieved on the vacuum state, we can't do any better than if we, well, since we apply the quantum limited amplifier, the output entropy of this can't be any better than the output entropy of the quantum limited amplifier. And even better, since this is an attenuation channel, I know how to use this to prepare the vacuum input to this channel. So by putting a vacuum into this guy, I prepare the optimal state for this channel AG, and that gives me the optimal output entropy of this guy too. Does that part make sense, or? You look angry. Oh, okay. Okay. Okay, and then what? Oh, and then you can use this to get the classical capacity, the minimum output entropy also of the classical noise channel, because it's just the limit of these thermal noise channels. So then we're done. Let me see. So maybe I'll just show you explicitly what this 2 and this 4, these are sort of where the action is, right? So maybe first I'll just show you explicitly what this complementary channel to the quantum limited amplifier is. So you remember this AG, in terms of its action on the covariance matrices, it just maps gamma to G minus 1 gamma, or sorry, to G gamma plus G minus 1 identity. And the action of the complementary channel of that, it's better to write down in terms of how it acts on the Hilbert space rather than covariance matrices, because then it's more clear that it's entanglement breaking. So when the complement to that channel just acts on rho, it's equal to this. Maybe, is that legible? No, okay. I should write it out bigger because this is kind of, it's worth seeing.
You can trade off between the size and putting little bit pressure on the chalk.
Oh, okay. Okay. And then I have to write down here so maybe I should just describe in words what this means. Basically, this is a channel that you can make by first doing a heterodyne measurement. So you do a measurement in this over complete basis. You get some answer. And then you prepare not that state that you got out, but some scaled down and phase conjugated version of the state. So you add a minus sign on one of the quadratures, but not the other. And then you add in an extra, well, scaled up rather, scaling up of the covariance or of the value that you get at the output of this measurement. Oh, this is a vector, and it's just psi1, psi2. So you just integrate over these two variables. Yeah. Okay, so that is sort of this part. We just saw how it implies that part. Maybe I'll say a couple of words about this. Basically, the idea here is if you take a I have the little lemma here. So basically now if you take the quantum limited amplifier and apply it to some pure state, psi, this has an entropy at least. H. This has an entropy that's equal to the entropy of this complementary channel acting on the same state. And that, it turns out, is going to be unitarily equivalent. This state is going to be unitarily equivalent, where the unitary depends on this. Well, actually, basically what I want to say is not only are the entropies equal, the spectra of the two states are equal. Oh yeah, the spectrum of this state is equal to the spectrum of that state. So there's going to be some unitary that maps this state to that state. And you can figure out what that unitary is. And you can look at, let's see, how do I put it? You can look at, up to a complex conjugation here, you end up with this state. It has the same spectrum of this, so it's equal to, or it's unitarily equivalent. But this state, up to a complex conjugation, is going to look like not A hat G, but AG acting on some further attenuated input state. Here. So what's the point? The spectrum of this is going to be the same as the spectrum of, I take the same input state, I attenuate it a little bit, I apply another quantum limited amplifier, the same value of gain, and a unitary, and I get the same spectrum out again. Okay? So then what's going to happen is,
Is it clear that you will be psi dependent?
You will be psi dependent.
Psi dependent.
Yes.
And how does one know that the attenuated, the AG acting on the attenuated side and AG acting on psi will have the same spectrum?
Because we know that AG acting on psi has the same spectrum of A hat G acting on psi. And then we can inspect this state and see that up to a complex conjugation, it has the same, it's equal to AG acting on an attenuated psi.
That part is not clear.
Yeah, okay. I agree that's not clear. But, pardon? Oh. But I think maybe we're not going to make it clear in the next few minutes. But we can, maybe we should talk about it either tutorial or tomorrow morning. But the point is, once you have this going, you can see that for any state, if you keep iterating this process, you're going to find that that by applying all these different unitaries, well, let's say if you start with some psi, you want to figure out how to make the minimum entropy. I think I wrote down some of the argument here. Maybe let's leave it at, you can use this fact to show that the entropy is minimized on the vacuum state, and that wraps up the proof. So now, I guess this is a good summary over here. This is a sketch of the proof. You take the channel, you decompose it into something whose complement is entanglement breaking. That makes the minimum output to entropy of that guy a single letter. You can show that the minimum entropy of that guy on a single channel use is achieved by the vacuum. And that lets us compute the minimum output entropy of the original channel again. Okay? So that gives us actually, now you can just evaluate what this Holovo information is. And it ends up being the classical capacity of the thermal noise channel with the energy constraint E. It's just going to be equal to the maximum of this mutual information under the constraint that we had. And this is actually going to be equal to the maximum output entropy of the channel minus the minimum output entropy This is achieved by using the thermal state that has the highest energy. So this is going to have, and it's going to have average output photon number equal to 1 minus lambda times E plus lambda times 2NE. Right? This is the average photon number of the environment. And this is just going to have, because I put in a vacuum, the average photon number is just going to be G of lambda NE. Okay? So this is the formula for the thermal noise channel. And maybe something interesting to do in tutorial is to take the limit when the noise and the power are high and see that you can recover the formula for the additive Gaussian noise channel up to a factor of a half. And that factor of a half comes from the fact that we've got two quadratures here rather than a single quadrature, which is what the single variable additive Gaussian noise channel was modeling. Okay, so tomorrow we'll look at some quantum capacities of Gaussian channels and also some entanglement stuff. We're done. Thanks.